Okay, so for record, two students in the class, one not in the class. Okay, right. Now today we're going to look at chapter 2. Okay, now chapter 2, we're going to focus on stiffness displacement method, where we will focus on stiffness matrix, the K, and how do we derive equation for that, and then we apply some boundary condition to the system. Okay, now let's look at the definition of a stiffness matrix. So in your tutorial, chapter 2, if you download and print out, so this one you will see in question 1. So what do we mean by element? Element is a simple system where you have 2 points and then you have a spring shape of element. So this is the free body diagram that we draw for a system. For example, if you have a steel bar, and this steel bar, when it's having load, and this bar is able to move to X direction, Y direction, and Z direction accordingly. So we convert this kind of system into this free body diagram. Okay, so where every time you see a circle, it means node. Node, and sometimes you need to draw your system into free body diagram in nodal presentation. So if you see the keyword nodal, then this means you need to focus on something with a small circle like this. Okay. Right. So previously what we learned, the equation that we learned is F equal to capital K and D. And again, the shape, every time you see the shape, curly shape bracket, it means matrix already. Yeah. So this is a square bracket and this is a curly bracket. So again, every time you see a formula with the bracket, it means matrix form. Okay, it means matrix form. And on the screen here, you will see the formula that we use here is a small alphabet. Means previously what we learned is a capital, but for an element we use a small one. Okay, the capital F will become the small f. So every time we ask you to analyze an element, you change a little bit from the equation that we learned. You put in a small letter. You use a small letter F, small letter K, and D to represent that you are calculating element. All right. So, okay. So, if you use a small alphabet F, it means you are analyzing an element at a nodal dimension. It means that at a node dimension. Okay, at a point dimension. All right, and also here. So every time I see you write equation, small f equal to small k times the d, means that you are going to process your data in a nodal dimension, or you are looking at a single element. Okay, single element. Okay, and of course, the middle one is means the stiffness matrix. So today we're going to focus on this component. Okay, this component. Now, another diagram that you see on the screen here is a combination or assembly of lots of elements. So this diagram you see on your screen now is three element that you have in the system. Okay, so when you want to analyze a combined system, we will use a capital F, capital K in your analysis. So again, we only deal with one single formula, F equal to K times D. Only when you write in your answer or in your solution, you need to be careful on the presentation that you write in. So if you're looking at single element, you use a small letter alphabet. For F and K, D is standard, displacement is standard, small d. But if you are analyzing at a bigger picture, we call it at a global scale, then you use a capital F, capital K. Is it clear?
Pardon?
Is it clear for both of you? Any question? Is it
A little
okay?
bit.
A little bit, okay. Okay, all right. So I'm going to ask you a question. Okay. Now, what is the okay? I'm going to ask Katana. So, Katana, what is the equation that we learn that we use to analyze uh, a system in this for this module? What are the equations that we learned in the previous lecture? The only equation that we learned.
F is equals to KD.
Okay, F equal to KD. Excellent. Okay, Lai, what is the shape of the bracket that we should use for F for our force? We have two types, all right? We have curly and square bracket. So what shape of matrix that we should use for our force?
Curly.
Curly. What shape should we use for K?
Square.
Square. Then for D?
Curly.
Correct. All right. Now, we know that just now in our previous slide, we know that we have two systems. One is nodal system with single element, and also a combination. It can be many, yeah. It can be like that. Okay. Now, just now we also learned about this one. F equal to KD also. Okay, I'm going to ask Katana also. Katana. So this question is for you. So if we use a small f in a formula, small f and small k, which one, this formula apply to which one? A single element or assembly system? Which one?
The single.
Single, okay, correct. So if you want to analyze a single element, mean that it in the, of course, in the test or final exam, you'll be given an assembly of a system. So you will start with the capital F. Then after that, you will focus on the individual system. Okay, you write this one first, and then you look at individual system. You break the system. So for example, you break this one is the element 1, element 2, element 3, element 4. So you write the first one, capital F, capital KD for the assembly, and then you break the system into element 1, element 2, element 1, element 2, means you draw out the element. Oh, sorry, not this one. Element 2 will be like this. Then element 3 will be like this. You break the system. Okay, element 4. Okay, right. Then you write the equation with the small capital F, KD, and this one represent the first one. This one represent the second one. Meaning you will have 4 set of equation if you have four spring like this. Okay, if you have 3 spring, then you have 3 equation. So if you have 4 spring, then you have 4 equation. So as a principle, you should know what we are doing. Okay, right, good, excellent. All right, so at least you understand what's the difference between these two formula. Okay, now we look at your tutorial question 2, where you see a spring system. And this spring system, what happened to this spring system? And again, if you see a small circle, or we call it nodal or node, all these small circle, we call it node, N-O-D-E, node. So we have node 1 and node 2, or position 1 and position 2. And every spring that we have also have a K. So we know that if you learn in physics, I think most teacher, they will use Kx. But in this module, we'll use U for displacement. Okay, we'll use U's for displacement in X direction. Again, I refresh. So you have, if in 3D, all the movement to the X, we use U, all the movement in Y, use V, all the movement to Z, we use W. Okay, so for the diagram that you see on the screen here, you have two nodes, a spring, a single element with two nodes, so node 1 and node 2. And also you have since you have a spring system, or throughout this module, every element that able to stretch and compress, you will have stiffness with the letter K. So K is a stiffness for this material. And in this spring, this element only move in X direction only. This is a very simple case. Of course, in your coming test, you won't have only X. You will have movement in Y and X, or maybe in Z. Okay. And what else? Okay. So, and then you are apply with the force at node 2. You see there's an arrow here. It means there's a force, or there's a pulling element. There's a pulling force that happen in node 2. And also there's a pulling compression force, or compress at point number 1. Okay, so meaning you have if you're given a structure, in question, normally you have a steel bar that pulling from one side and compress from one side. So you have a force for the point number 2, force point number 1, and then you convert the physical system into a free body diagram like this, like spring system, like this. Okay, and if the point, the node 1 or 2 can move, means that we will represent the displacement with U. Okay, U means displacement. So U also means that every time we write the word, the alphabet U, it means that the structures is moving in the X direction. Okay, so if you accidentally you write V, it means that the node is moving in Y direction. If you accidentally write V, means that the node is moving in Y direction. Or if you accidentally write W, it means it moves in Z direction. So be careful on the displacement unit that you use in your answer. Okay. And a small detonation, it means that if you write U1, it means displacement in point 1. And if you write U2, it means displacement at point 2. Okay, let me see. Okay, Katana, I mute your mic first, because we are recording the sound of your taking notes. Okay, so U, and then the F1 means that if you use a small capital F, it means the force at node dimension. At node means we focus on this small point only. If you write F, capital F, it means the global scale, means structure, the what you call the general structure. For example, if you compress, if you have a spring, and in physical system you compress with a force, then we use capital F. If you want to study the dimension in this point only, so if you draw in free body diagram, single element like that, So every time you draw a single point like that, we use a small f. Okay, so be careful on the alphabet that you use in your answer. So if you use a capital F, it means that you look at the bigger picture. If you use a small f, you look at a smaller picture. Okay, be careful on the notation that you use in your answer. And the length of point 1 to point 2 given by L. All right. So any question on the diagram itself? Ask me question if you're not clear or you quite blur or you don't understand what I'm talking about, you ask me question right away. You don't understand anything that you see on the screen right now. The F1X, U1, what is 1, what is 2, what is K, what is L, and what is all these alphabet. Anything that you're not clear, ask me now. Any questions so far?
Not. But
Lai, you
maybe
okay? Lai, you okay?
Oh, okay.
Okay, huh? Okay, hold. Okay. All right. So I explained already what is a node. Okay. Now we're going to look at a new matrix formula for today. So we're going to convert all this diagram into a matrix form. Okay. So we will put, because we know that the general equation that we learned for this chapter, we know that F equal to KD just now. We will keep repeating this formula. We're going to expand what we have in our system. Now, for example, in this system, you have two forces. So F1x, F2x. So you write what you see in the system, you put inside the bracket on the left for the force. So on the force component, you have F1x, F2x. And then the stiffness matrix, I'm going to explain later. The displacement, D, after we expand the equation, we will write U instead of D. So of course, in exam, if you write D1, D2, you get the wrong answer. If you write D1, D2 in this area, so be careful. So this is displacement. So when you write in the matrix form, you have to tally with your free body diagram. So for example, movement in point 1, movement in x direction, we use U1. So make sure when you write your mathematics model, your displacement refer to point 1 is U1. So write U1 instead of D1. So be careful on this one. Okay. Now, we're going to explain what is, how do you build this stiffness matrix now. Okay, so for stiffness matrix, because, okay, before I explain, so if you look at this element, if you look at point 1 and point 2, and point 1 and point 2 are free to move, means that this spring is able to move in one direction S, X, and one direction X. So you have a two degree of freedom inside the system, meaning you have point 1 able to move in X direction, point 2 were able to move in X direction also. So your matrix will have 2 times 2 dimension. Okay, we're going to look at this one. So the stiffness matrix here, we have 4 value of K, stiffness matrix. So K11 means column 1, row 1, right? Sorry, row 1, column 1. K12 means this is the row 1, column 2. Okay, row and column. You have to know the matrix. And K21 means it refers to the row number 2, column number 1. So K22 means column number 2, row number 2. So these are the coordinate or where you should put your K correctly. So this is the general equation that you should have. If you have 2-point system, then you will see 2 force on the left, 2 displacement on the left, and 2 means you will have 4 unknown or 4 stiffness inside the matrix in the middle. Are you able to see the logic why we put this equation together? Okay. So later we see example. Okay. So again, if you use a small f, it means node or nodal dimension or nodal force. If you use a u, it means also displacement. U to represent displacement in x direction. If you use v, it means y direction. If you use w, it means z direction. Okay, so of course in your final exam or exam, it won't be that direct. Okay, I'll give you a direction. I'll change the x into maybe y or z. Then this one, if a system I give you in the y direction, and your answer you give me the displacement in u1, u2, you get the wrong answer. Okay, if the system I give you in y direction, your displacement you should change to v1, v2. If I give you z direction, then your displacement will be w1, w2. Is that clear for both of you?
Yes.
Okay, good. Excellent. Okay. Now, from the matrix itself, we can tell the degree of freedom. So, if you write like this, we know that point 1, you only have one way of movement because you only have a u1 in this direction. So, and f2 also a one direction. So you only have 2 displacement inside the system, either point 1 or point 2. You have 2 degree of freedom. And for this, throughout this module, if you draw out the axis, right, all the direction to the x to the right, left to right become positive. All the direction going up is positive. All the direction to the z direction or z axis is positive. So just take note, because later on, sometimes the force will become another direction, then you get the negative. You'll see this one in the example later on. Okay, we have clear with a simple system, spring, 2 node, and then free to move around. Means that point 1 able to move in one direction, point 2 able to move in one direction. Okay. All right. Now the next diagram. If you look at the, hold on now. There's a new message coming in. Okay. Now you look at the screen now. We are having a different system now. You have a spring system. Again, a spring system here represent a bar, a steel bar, or a material that able to expand or contract when you have a temperature or you're able to pull it in the physical world. Okay, so we represent a steel bar or aluminum bar into a free body diagram like that. Okay, again, I repeat. So Hooke's law gives you kx. In this module, we represent the displacement here according to the axis they are. So again, x we use u, y we use v, z we use w. So I'm going to repeat this one many times. So for this system, if you look at the diagram, you know that again we have a simple system element. So every time you see a small circle or node, you know that every time you recall this equation, F equal to KD. We're going to repeat this equation so many times until you can memorize. Huh? Okay, so every time you see a single node like this, or you analyze the system in a node dimension, then you straight away you write this equation, you get 1 mark. Huh? So for example, if you see this system, you write this one, you get 1 marks. And this system is moving in the x direction in point number 2. Okay, in point number 2, spring also have a stiffness matrix, and the length, the length or the length between the distance between point 1 and point 2, or node 1, node 2, given by L. After that, this spring was loaded with a tensile force. So if you're given a structure, every time you hear the word tensile, T-E-N-S-I, tensile, or T, it means you're pulling away in a different direction, where at the end, your body will elongate. Another force that you learn in stress analysis is compression. It is C, compression, right? So when you compress, the elongation will become negative. The size will become shrink into a smaller size. Okay, so this is the elongation. This is the elongation. All right. Now we look at the diagram on the screen now. So point 1, you have a tensile force which is pulling to the left hand side. Point number 2, you have a tensile force pulling to the right hand side, and you're given a general axis where positive direction to the x is from the left to right. Okay, now I'm going to ask question by looking at the diagram. Okay, so point 1 will move with a displacement u1. Point 2 will have a displacement of u2. Now, if you have a t value, if you have a t value here, let's say your t equal to 100 Newton. Okay, Katana, what is the value of t here? What is the t value you have in point 1?
It will be same.
What is the value?
100 Newton.
Okay, and it does. Is it positive or negative?
Oh, if this is positive, then yeah, this other direction, negative.
So it will be t equal to negative 100 Newton.
Yes.
Okay, good. Now, next question I'm going to ask Lai. So if you look at point number 2, you have U2. What is the U2 means to you? What do you understand? What is U2? Lai. Like, what is U2? Okay. Okay, I'm going to guide you through. Okay. Like, what is the equation that we use that we learned so far? What is the only equation we learned?
F equal KD.
F equal KD with the curly square and curly bracket. What mean by D?
The displacement.
Correct. So what is U2?
Displacement.
Displacement at what point?
U2.
Okay, correct. Now, let's say you have, you know that when you pull to the x direction, your displacement, is it positive or negative, line?
Positive.
Positive. Now, if you look at point 1 here, diagram, and the diagram gives you this direction, it means that you assume all the value, if your value is positive, this point we're going to move in this direction. Correct? Correct,
Yes.
Lai? Yeah. Now, you know that when you pull physically to the left, what happened to the value of U1? Is it positive or negative?
Negative.
Negative, correct. So it means that when you, in your calculation later, you will see U1 will be negative, T1 will be negative. Although the diagram draw like that, means that the diagram, when before we know, we go further analysis, we will assume the direction of the point. So if the direction is positive, you draw like that, and then you get the answer is positive. For example, you get U1 equal to negative 3 meter, displacement 3 meter. It means, what does this negative means? It means that what you assume in the diagram here is wrong. Means that in reality, in your final answer of your analysis, point 1 going to move in this direction. If you calculate until the end, you get U1 equal to negative 3. It means that when you draw your free body diagram back later on, when you present your results, your U going to this direction. Okay, try to understand what we're trying to do. So it means that your T value is negative 100 Newton, because is the opposite direction of your x axis. However, when it comes to your displacement, so in the diagram, before you do any analysis, you just simply give a direction of the assumed direction. Let's say you assume to the left your U1, and you do your analysis. At the end, you get U1 equal to negative 3 meter. It means that this answer, it means that this is the initial assumption. You assume, before you do analysis, you assume that U1 will go this direction. But when you do analysis, after that you get negative, it means that in real life, your point 2 is moving this direction. And if you redraw your system in this direction, your answer U1 will be positive value. You get the concept? Why this case we use negative? Why this case we use positive? Lai or Katana, do you understand what we are discussing?
Pardon?
You understand what we are discussing so far?
I think I was left on the displacement value of negative 3 meters.
Okay, so you
Build the
still blur
assumption.
on that, is it?
Yes.
Okay, now I'm going to explain. So let's say you have a spring system, and you have point 1 and point 2, correct? And then you know that okay, let's say we pull from two sides, we have a tensile force, put two sides, and you have x direction and y direction. So you know that before you do anything, you know that point 1 will move, right? Point 2 will move. So Katana, you understand why we use U or not? Why we're not using V? What we're using, not using W? Why you use
Uh,
U?
X direction displacement.
Correct. All right. Now this is the let's say, and you also understand that why later on your value of T will become negative because of opposite direction. Now we focus on displacement. Now, before you do analysis, let's say you assume the direction of displacement is to the left for both points. Let's say you assume U2 and U1 both to the left. Okay. So, and then let's say you get let's say you know that the displacement of point 2 will be 3 meter, let's say. Okay, and then you're going to solve what is the displacement at point number 1. Okay, so you do solve lah. You do your calculation. So at the end, I mean, logically, you know that what is the direction of point 1 will go? Will it go to the left or right? To the left or right? Katana? Point 1 will go to the left or right?
To the, pardon?
If you're given the force, the tensile force at point 1, like what you see on the screen here, what is the
Yes.
direction of the displacement? Will it go to the left or right?
Left.
Go to the left, right? So logically, you know that this point will go to the left. So when you solve your mathematics model, you'll get point 1 equal to, let's say, negative 1 meter. This one, I mean, you solve lah. You know that technically you will go to the left. But in your earlier assumption, before you do your mathematics calculation, you draw on a free body diagram. You go to the left, go to the right. Sorry, for point 1, and then you go and solve. You use F equal to KD. Later we'll look at the detail. Now I try to clear your doubt. So you use this equation to solve, and then at the end, you reach at the answer of U1 equal to negative 1 meter. What does this mean? Why there's a negative there? It means that what you draw on a free body diagram is wrong, or your answer do not agree with the direction that you draw on the free body diagram. Does it make sense? It means if you substitute the value inside the diagram, let's say you have T1 and T. So U1 equal to negative 1 meter, let's say, correct? And U2 equal to 3 meter. This is what you solve from the early beginning. You solve, and then you get the answer U1 equal to negative 1 meter. So you rewrite back what you calculate, U1 equal to negative 1 meter. You understand so far, Katana, up to this stage?
Yes.
Okay. Now you look at the answer that you have in your calculation. All right. So what does this presentation means to you? U1 equal to negative 1 meter. Why there's a negative there?
Because it's in the opposite direction.
Correct. So when you try to solve question, be careful on your free body diagram. So if you early in the first diagram that you draw, you just stick to it. You just stick to it. For example, in the early beginning, you assume that all the displacement were to the left in x direction. And if you calculate, you get a negative, you just continue to use the negative number. Like this. Okay. But, let me erase. Okay, so far you understand up to here. And then, okay, this is your, up to this stage is your calculation. From here to here is what you calculate. Let's say you use a formula to calculate a system like this, and at the end you get U1 equal to -1 meter. So this is your calculation. This is up to your calculation. And of course, when you communicate with your colleague later on when you go to work, you won't tell your customer, hey, this point moved -1 meter. You won't tell like that one. You won't tell people like that. So you will tell that your customer that according to your analysis, if you have a tensile force, it's going to move in this direction with the 1 meter. And this one move to here, U2 equal to 3 meter, for example. This is in real life or correct version. You understand now? The difference between this one and this one. Katana, do you understand? The difference between the one on the left and right?
Yes.
Okay.
Yes.
Yeah. So my advice to you, so don't simply change your free body diagram in your analysis. So if in the early, if you already assume that the direction is to the left, then you continue to use the free body diagram that you use and use the answer that you calculate. For example, in this case, you get the U1 equal to -1 meter. Continue with this assumption until you get all the unknown. Okay, until you get all the unknown. Don't change, don't you calculate here, then you go and change the free body diagram. Then you are going to confuse yourself. Okay, it's just that you need to understand what is the meaning when you get a negative. It means that what you assume in your calculation earlier is wrong. It means the direction is wrong. So for this case, in the early you assume 0.1 will go to the left. You calculate, then at the end you get U1 equal to -1 meter. It means that what you draw in the free body diagram here, U1 will go to the left. All right. So of course, in this module, most of the time I will ask you the meaning of the value that you calculate. All right. For example, you calculate U1 equal to -1 meter. So I'll ask you, will the 0.1 move to the left or right? So you explain based on your answer and explain why. So you just explain 0.1 will move to the left because in an analysis, the answer U1 equal to -1 meter. Yeah, so because all the direction to the X direction to the right is positive, and my answer, I get negative. So in reality, 0.1 will move to the left. So this is how you answer your question. All right. Lai, do you understand what we're discussing so far?
Yes.
Can Katana, do you understand what we discussed so far?
Yes, sir.
Okay, good. Okay, we go for maybe 1 or 2 more slides, then we have a short rest. All right. Now again, we recall the 7 steps that we learned previously. So first one, choose the element type. So we have 2 point, 3 point, 3D, symmetrical. So what do you think? Which type that we are using? Katana?
For this,
Yeah, for this, for the diagram that you see on the screen here.
this is the 2-point, not 3D.
Correct. This is a 2-point type system. So choose the first one. So we only have nodal system. All right. And then the second steps, we go for equation, displacement equation. So we know that equation, how many equations do we have? We have linear equation, quadratic equation, polynomial. So we know that spring equation we only have one, F equal to KD or KX, right? We only have one. So this is a linear equation or quadratic equation or polynomial equation. Like F equal to KD, what is this type of equation? Linear equation, quadratic equation, or polynomial?
Easy linear.
Okay, correct. The answer is correct. So again, you will have linear equation. Maybe the term you're not familiar. Linear means y equal to mx plus c, which is a straight line, like that. Is a linear. So, and then quadratic, y equal to ax squared plus bx plus c. This is quadratic. Poly means this exponential component here more than 2. Y equal to x3 plus so on. Okay, so we only have kf equal to kx or Hooke's law, or in our matrix form, f equal to kd, displacement, force equal to stiffness matrix times the displacement. So this is a linear equation, y equal to ms plus c. Okay, so of course here our c here value here is 0 lah. Okay, so we only have y equal to mx, or right? So you should understand what type of equation that we're using. Okay, step number 3. Again, recall strains and displacement relationship. Strain equal to du over dx. Or recall when you learn about strain. Okay, delta L divided by L. So we just change it to another mathematical form. Strain equal to du over dx. Again, u here is a displacement in x direction over dx. And stress, you use a modulus Young. Stress equal to E times the strain. Okay, you should be able to recall this. All right. And here we use the different symbol for the displacement. We use the sigma or delta. Okay, we use this symbol to represent delta. So let's say you have a displacement 0.1 and 0.2, u2 minus u1. So your displacement or elongation, why we use the word elongation? Because we have a tensile force. You're pulling from both sides. So when you pull this spring, you're going to have displacement. Displacement or deformation equal to, you take the u2 minus u1, you get your displacement. Okay. So far, any question, Lai? Anything you want to ask me?
No.
No, okay, good. Okay. So now, why we have a negative here? I already explained. Because your u1 in your calculation, you know that 0.1 will move to the left. Because you pull from 0.1 to the left. Displacement at this point will move to the left. So x direction positive to the right. So your u1 will be negative. Okay. Yeah. And the equation for our system here, tensile force equal to K delta, which is also the same. F equal to KD. It's the same principle. So F equal to KD, you transform to the formula that we have here. T equal to K delta. So you replace what you have here, T equal to K times U2 minus U1. Okay. Any questions so far up to this stage? Anything that you don't understand? Why? Why certainly negative here? Why our formula become T equal to K U2 minus U1? Any area that you're not clear? Ask me now.
Nope.
Yeah. Okay. Good. We move on. After that, okay, this one covered already. After that, we derive the stiffness matrix and equation. Okay. All right. Now we're going to look at this diagram. So a spring again, 2 point, and then this is L is the original length, and you know that after you're pulling, point 1 will move to the left with its U1, point 2 will move to the right with U2. So try to understand what happened to the diagram that I show on the screen here, right? Why suddenly you have a U1 to the left, U2 to the right. So this is after you do adjustment to the diagram. So first diagram here is the original spring. Second diagram here is under the effect of loading, right? Loading means you have a tensile force on both sides. And this is the arrow that you put in your early assumption. And this is the third diagram here is what is your expectation. So it will move to the left for node 1, move to the right for node 2. This is a more logical sense diagram. Okay, so we're going to put in the equation that we know so far. So don't worry about the mathematical model. It's as long as the diagram makes sense to you, you're able to write all this equation out. So we put in what is the force, right? We're going to focus on F equal to KD again. So small f means we look at an element. So F1x equal to negative T. Again, you should be able to understand why we have a negative T for 0.1. So F1x means force at 0.1 with the value of negative T. Why negative T? Because your T is moving opposite of your x direction. And force as 0.2 is a positive T. Any questions so far for your force component? Katana, you all right?
Yes.
Okay, good. Then we want to put everything in a T form. Means we will move our T to the left. Means you rearrange both equations. So we put the T equal to negative F1x and T equal to F2x. You just what we're trying to do here is we try to put everything in the same dimension. So we focus on the tensile force, the T equal to F. And then we put in what we understand so far. Okay, so because just now we define what is our T, right? T equal to K U2 minus U1. You just put inside the equation. You just substitute inside the equation. So both sides will give you the same equation because both negative 1x equal to T, F2x equal to T, so both equal to the same equation. And then, okay, so the next equation I'm going to show you is on the left hand side, because you have a negative, you put the negative from the left to right, your equation is going to flip over. So you times the negative on the left, both sides, times negative here, you're going to get negative KU2 and positive KU1. And you rearrange the equation, you get K times U1 minus U2. Lai or Katana, you are right with this equation?
Yes.
Understand why suddenly we flip the equation? You should be able to understand. Lai, you understand?
Yes.
Yes, okay. So these are the area that student will make mistake in the exam because they don't understand why they just use they forget about the negative and then they continue to do calculation. Then the whole the calculation at the back will be wrong. Okay, so this is important. So just to highlight that one. Okay, then F2, you just continue what we have here. So we have a two equation here. F1x equal to k u1 minus u2, f2x equal to k u2 minus u1. So we have these two equations so far. Okay, right. Then we put into a matrix form. How do we put in a matrix form? The matrix form that we talking about here is F equal to K D form. Curly, square bracket, curly. So we want to put in the expanded format. So you're going to put from this one into here. Okay, you should able to know how to put the equation into matrix form. This is a 2 by 2 matrix, which is quite easy. So on the left is a force. You have two force here, F1x and F2x, equal to stiffness matrix times the displacement U1 and U2. So it should be no problem for your F and displacement. Okay, I'm trying to explain a bit on the matrix. How you calculate matrix? You know that your F1x equal to, okay, I'm going to expand the first equation. F1x equal to k u1 minus k u2. So how do you put in the matrix form? You know that you have 2k here. So you look at your matrix as a coordinate system. Let me draw the coordinate for you. So the first row here, the first row represent u1 dimension. This row, sorry, not row. This column represent u2 dimension. This row represent u1 dimension. This row represent u2 dimension. Okay. Now, how do you get this equation put into matrix? How you calculate? So I'm going to erase all these coordinate so that you can see it better. So how you get the value? The first step, you times k times u1. First step, k times u1 in the first step plus negative k times u2. So at the end, you get k u1 negative k u2. Does it make sense to you? Katana, live?
Pardon again?
You
Sorry.
understand? You understand?
No, sorry, I was touching the screen. the line just below the linear equation.
Okay. Okay. Live, what about you? Do you understand why suddenly this one we can get the answer?
A little bit.
Okay. Let me explain one more time. Okay. I'll start from the matrix dimension. Okay. Now, you know that your general formula that we learned, F equal to KD, and when you put the bracket in, means that you are defining the formula in the matrix form. So we only have two equations so far in our system. So force, we know that you have F1x and F2x. Displacement, you know that you have two displacement inside. You have U1 and U2 so far. Any questions so far for F and for your force and displacement? Any question, Lai or Katana?
Nope.
Okay, so far clear. Huh? All right, I'm going to go into the stiffness matrix now. So in the matrix for your stiffness, which is your K, it will be like a Lego or it will be like a map. Huh? So I break my my matrix into 4 coordinates. So column here will refer to your U1. U1 means that K and negative K both represent, it will relate to U1. Then the column 2 here, negative K and K here, will link up with U2, right? So negative K and K at the column 2 here won't deal anything, won't have any relationship with U1. Okay, so we have deal with column here. Column 1, column 2. Column 1, it only cares about U1. Column 2 here only cares about U2. Now we're clear with the column. Now we deal with the row in the matrix. So row number 1, row here, it means the movement of my cursor. You'll see the K and K. I move horizontally, my mouse cursor. So this row 1 will only interested in U1, means here, all right? U1 value. You don't care about U2 for the row 1. So row 2 will only cares about U2. Try to understand the coordinate, or where does all these element or all this value will link up. Okay, so in a matrix, you can break into coordinate. So let's say you have A and B unknown that you want to find. So this column will link up with A. This column will link up with B, and then this row will link up with A. This row will link up with B. Do you understand the concept? Katana,
Yes.
you understand?
Yes.
Lai, you understand? Okay. Now, going to a bit more detail on the formula. Now, how do we expand our matrix into a formula? Or how do we put our, okay. So when you calculate, okay, let me explain the general. Okay, let me put as A, B, C, D, and E and F. So how do we put this matrix into a formula? So the first step is that you take A times E, first step, plus you jump to the next step, B times F. This is number 2. So this is step number 2. So you get the first equation. So you get AF times BF. So far you understand what is happening here? Katana or Lai?
Yes.
Lai, you okay?
Okay.
All right. Now you put this concept into this formula. So you take K times U1. What you get? You get K U1 plus This is step number 1. Plus this element times U2. So you get negative K times U2. So at the end, you rearrange this equation. KU1 negative KU2 because you just expand the equation. Then you get the equation you have for the first one. The first row, the first row times the first column, you will get the first equation for the first one. F1x here. So far, you all right? Katana and Lai?
Yes.
Lai, you all right, huh? Lai, which area you still don't understand?
Okay.
Lai, okay, huh?
Okay.
Ask me question if you're still not clear, because later on it will become more and more complex. Clear all your question on the screen now. If you don't understand, ask me now. So because if you confuse here, you're not able to do the following question. So just explaining how you get the two equation, and then you convert these two into a matrix form. So the force on the left, displacement on the right, and then you put stiffness matrix K minus K1, right? So here, maybe this one confused you a little bit. What I usually do, I will use this one, I will rewrite this one as negative KU1 plus KU2. Then I know, then I can compare these two equations to write in the matrix form. Maybe I write in this form, it make more sense to you. Because if you put in the same format or same form, because you start with F, KU1, KU2, and the second equation also F, KU1, U2. Of course, there's a positive negative sign there, but they are in the same format. Then after that, you convert these two equations into a matrix form. So how do you convert into a matrix form? First equation, you look at this one, and then you take this one, this section, and this section, you get the first equation. And then the second equation is this one. You take this one times this one. Then you get second equation. All right. So far, both of you all right, huh? Ask me a question if you don't understand. So we know that this one, we call it stiffness matrix. We call it as a stiffness matrix K. And we start to look at the word local. Local stiffness matrix because we are using small alphabet in our formula. And why we use a small alphabet in our formula? Because we are looking at element. It's not a very combination of many springs. This is only one spring. So that's why you use a small f, small k. So in the equation, in the matrix here, we're also using the small f, small k, and small u. Okay. And why u? Because it's moving in the x direction. So again, all the movement in x direction, we use u. All the movement in y direction, we use v. All the direction in z direction, we use k. So if this question, I change it to y direction, so the displacement component here, we use v instead of u. And if I change the direction to z, you change the displacement formula here into w, not k, sorry, w. Okay, right. So you need to refresh your understanding in matrix. Go to read appendix A. So if you look at this format, you get k, k, negative k, negative k. So The diagonal direction is the same. So k, k, negative k, negative k. This kind of behavior, matrix behavior, we call it, we have a symmetric matrix here. We have a symmetric matrix here, means diagonal is the same. And also it's a square. Square means 2 times 2, 3 times 3, 4 times 4. It means you get A, B, C, D is a square. You get A, B, C, D, E, F, G, H, I. 3 times 3. You get a square matrix, means a square shape, and 4, so on. And if you have this form, means you have a square plus a symmetric matrix, you get a singular matrix. So if the word singular matrix you are not clear, go and polish up your matrix understanding. And if you have these three scenario come together, the determinant of this matrix will become 0. So if the word determinant also you're not very familiar, go and read up notes in your calculus or advanced mathematics. What is determinant for matrix? Okay. Then you assembly them into a global equation with a boundary condition. Okay, this is just a mathematics formula. So it means that if you see this big symbol, it means sum or assembly. Sum or assembly. K, it means the stiffness matrix that we are looking at. E means element. So it's a combination of many elements. Stiffness matrix K1, K2, and so on inside here to become the global. Become global. So I break it into 2 dimensions. So let's say you have a big system with a 4 spring. Then the one on the left will be the stiffness global stiffness matrix. And the one on the right hand side, the mathematic model here, means you break your global into a small pieces of element. Element 1, which is here. And then you break into second pieces, element 2. That is element 2, element 3, and element 4. So it's a combination of element. Okay, and same with the force also. Same with the force also. So this is just a mathematics writing. Okay, at least you look at the mathematic model, you know what does the mathematics meaning. Okay, this symbol means sum. This one means element. This one means global. Okay, and then you solve for the displacement, step number 6, and then you solve for the force. Okay. All right. Any questions so far? I think we stop here. Then the next class we'll look at an example. Okay. Let me stop the recording.